So far we have discussed about digital modulation technique introduction. Okay, in that introduction we have seen the definition of digital modulation. We have seen classification of digital modulation. Okay, now we are going to discuss the very first very first technique of the digital modulation, that's known as BASK, binary amplitude shift key. Okay, so now we will discuss binary amplitude shift key. In this technique, what actually we does, we have got a carrier and the digital signal. Okay, the digital signal actually modulates this carrier. We know the digital signal, we have already written, it's a binary amplitude. That means it have got two message signals, either 1 or 0. That means it would modulate carrier either at 1 or 0. That means for a bit duration dB, it would transmit a signal 1 or 0. That means we will see it in the pictorial wave onwards. So let's first discuss what is it's also known as on-off key, because the digital signal modulates the carrier such that it switches on and off according to digital signal. Okay, as in the digital signal there is 1 or 0, accordingly the carrier is also set. Okay, that's why it's also known as the on-off key, because it behaves like on-off. Okay, on-off switch. Now what it does for symbol 1 in the digital signal, it transmits a carrier that is equal to the voltage of which is equal to root of 2ps cos 2 pi fc, 2 pi ft, where f is the frequency of the carrier, and this root of 2ps, it's actually the amplitude. We know the power of a signal is given by amplitude square upon 2. Okay, so that when we are going to it's equal to actually amplitude square upon 2, so that when we are going to substitute here amplitude, it would be equal to root 2 ps. Okay, that's why actually we have the signal a cos 2 pi ft, and here we have substituted in place of a root of 2 ps. Okay, so when there would be symbol 1, this very carrier would be transmitted of this voltage. Okay, when there is symbol 0, no signal will be transmitted. Okay, now we will discuss its waveforms. Okay. Now let's see here. It's here binary sequence unipolar RZ. That means it is the first here the binary sequence. Okay, here 1 and 0 is transmitted of the digital signal. It's like the digital signal. Okay, now it is represented as unipolar RZ. Unipolar means it has only one polarity, that's +1. In bipolar we have got two polarities, +1 and -1. At that time here we have only +1 voltage. In that very case we have also -1 voltage too. Here it is only one polarity. Okay, it's unipolar. Now RZ means actually it's here NRZ. It's here NRZ. Okay, binary sequence unipolar NRZ. Okay, NRZ means not return to 0. In case of RZ, after the half time duration, what happens, the signal comes to 0, while as in case of NRZ, that's here, it does not return to 0 after the half duration. You are here actually seeing that the 1 is for all over the duration. Okay, in RZ, for the half time it remains 1, and in the half time it returns to 0. Okay, so it is binary sequence in polar NRZ representation of the digital signal. Then after we have carrier signal. Carrier signal, you are knowing, it's a sinusoidal signal. Okay, sinusoidal signal. Then after this binary sequence or the digital signal modulates this carrier, so that gives the BASK signal. BASK means the binary amplitude shift keying signal. Okay, what happens here, you will be seeing here, for the time duration when it's 1, when there is 1, that means when there is output of the digital signal, the carrier is also passed. Okay, the carrier is present which equal to whose voltage is equal to root 2 ps cos 2 by ft, okay, where f is the frequency of the carrier. Then after, for the time duration, when here is 0, no signal is transmitted and here is gap in between the two pulses, okay. Then after, again for the for the binary 1, again carrier is transmitted, same carrier is transmitted again at the for the third one, okay. And in between these, whenever there is 0, no signal is transmitted, okay. It's all about the representation of the, it's all about the waveforms of the Bask signal, okay. Okay, now we'll discuss generation of ASK signal, amplitude shifted keying signal, how it's generated. Simply, we use a product modulator or the balancer modulator. Uh, the two inputs are one is the carrier signal and one is the digital signal. Simply, the two signals are applied to the two inputs of the balancer modulator, and at the output of the at the output of this balancer modulator we get ASK signal, okay. We are getting ASK signal, amplitude shift keying signal. That simply the digital signal modulates the carrier, okay. It's all about it is generation. Then after, what happens after generation to the power spectral density? It's almost the same as that of the original message signal, as that of the digital signal, but the only difference is that the spectrum is shifted to the two frequencies, plus fc and minus fc, okay. What it means actually, since you have already studied amplitude modulation, in that very case you would have studied that how the frequency impulses of carrier were present in the DSP signal, double sideband transmission, okay. So like that, here the two impulses are present at plus fc and minus fc of that carrier, okay. So it shifts, so here we see the spectrum is shifted to higher frequency, and that was our goal. That was the limitation of the basic baseband transmission, that in that very case we were not able to transmit a signal over high frequencies, so that we were not able to transmit it through high frequency links like radio links or satellites. And that's here the advantage of it, that it shifts the frequency, it shifts the frequency. Here the frequency is high, okay. How it's attained? This is by multiplying this carrier to it, and here the frequency is shifted, okay. This is about the generation of amplitude shift k, okay. In the next video lectures, I would uh, we would now discuss here the detection of ASK signal and some advantage and just disadvantage, okay.